Through our AML conversation series, we've covered a wide range of topics, from terrorist financing to wildlife trafficking, organ trafficking, to university-level training for the next generation of bankers. One of the evolving areas in AML compliance is artificial intelligence. We have published a number of blog posts and a white paper about elements of AI. As the use of AI and AML compliance advances, we will continue bringing you insights into this developing technology. Today, I'm talking with Stephen Cohn from Basis Technology. Steve is going to help us understand the basic vocabulary of AI and how AI is being applied to compliance today and how it will be applied in the next few years. I think you'll find our discussion interesting and informative. Thanks for listening. I'm here today with Steve Cohn. Steve is the Executive Vice President and Chief Operating Officer and a co-founder of Basis Technology. And Steve, thank you for joining us today. We're going to talk about artificial intelligence and help our audience understand some of the key components and how those can be applied to their work in the anti-money laundering compliance community. So before we launch into the details, why don't you give our listeners a little bit about your background?
Sure. Well, I started and still consider myself to be a technologist. Graduated just a few years ago, or a couple of decades ago, I guess, from MIT, and had an interest way back when really in two things. One is technology, and the other is human language. I had spent a year in college overseas in Japan, really enjoyed that, and was able, after a couple of other positions through my career, to connect with someone else who shared those interests, Carl Hoffman, the CEO and founder of our company. We started focused on, again, technology. He was also an MIT grad, and human language, and very quickly moved into building technology around human language, which took us right into the AI and machine learned space.
So one of the things that I know I've experienced as I've become somewhat more knowledgeable about artificial intelligence is it has its own vocabulary, as many technology areas do. So I think it would be really helpful if you could clarify some of the definitions. So let's start with the term itself, artificial intelligence. What is that?
What it is very loaded. It is just one of those terms you have to be very careful with, and honestly, there's probably almost as many definitions for it as there are people claiming to have definitions for it. I'll give you my perspective on it, and that is artificial intelligence is applying technology, and by which we mean software and electronic technology or software and hardware technology, to solve some form of cognitive or human cognitive problem. Those problems vary quite a bit, and they range at, I'll call the lower end, to doing some form of understanding of human language, the kind that I said we focus on, to vision tasks. This is the kinds of things that you see a lot, maybe on the evening news, being able to recognize types of images, or going to a web search engine and saying, show me red barns, and actually getting a pretty good result of a lot of red barns. Or to something else that I worked on in a previous employment, simply measuring in industrial applications, measuring the distance or the size of various things on being manufactured to be able to improve the manufacturing process. Those things, understanding human language or being able to process an image from a camera and come up with some sort of interpretation, those are cognitive tasks. Those are the kinds of things that we are proud of as people to be able to do. And artificial intelligence is when we become perhaps a little bit scared when we discover that machines can do certain of those as well.
Another term that I hear a lot is machine learning, or ML. Can you tell us a little bit about that?
Sure. So machine learning is essentially an underlying tool used to build these artificial intelligence capabilities or applications. What it means is through various and sundry different models that more or less simulate how the human brain is put together, we can produce a piece of software that has some ability to take an input, or maybe a lot of inputs, anywhere from tens to maybe thousands of inputs. Those could be images, those could be text information, lots of different possibilities for what those inputs look like. And by virtue of being told which ones are correct or which ones are not, or in an image, which ones show a picture of a cat and which ones don't, develop a statistical model of the inputs that is received to be able to then predict based on an image or an information that's never seen before, whether it's showing the thing it's been told about. To my mind, this more or less models the way we would teach a child something. And the sequence of steps that I think most people are familiar with, where parents will point at an animal in the field and say, cow. And the child, after seeing several of them, will be able to point at a cow and say, cow. The following step is normally something along the lines of a child pointing at a horse and saying, cow. And then the parents will say, no, horse. And you can watch sometimes the kid saying, or thinking, that's interesting. I thought that was a cow. What differentiates that? And in this, the child is building some sort of internal model saying, oh, okay, a cow has some features, be it spots or it's shorter and wider than a horse. So it can learn to differentiate. And after time, they'll point at a horse and say horse, and a cow and say cow, and so on. That's the machine learning is the software that emulates that learning process by being shown these correct and incorrect examples. And where do those correct and incorrect examples come from? We have people tag or annotate them. That's the term of art, is annotation. We have a lot of people, or some number of people, say, this is a horse, this is a cow. Show those images. In the case of image recognition, show those images to one of these machine learned tools and have it figure out what are the things that differentiate those two.
Another concept that I've heard described repeatedly is robotic process automation, or RPA. What is that, and how is it different from machine learning?
So RPA is kind of exactly what it sounds like. It's robots applied to process automation. Process automation, there's a variety of other terms for it, is building a system that takes a process, could be a manual process or a somewhat computerized process, and putting some automation around it, meaning making it so that it's easier to go from one state of this process to the other. Classic ways to do this would be having someone embed some form of rule saying, if this piece of information has been added to the data set, then we move on to the next one. If we have gotten a valid license, a driver's license number from a customer, well, then we have enough information to process an onboarding, for instance. Robotic process automation adds artificial intelligence into this in the same way I just described, where you have a machine observe a human executing a process so that it can figure out what are the required information, what are the required steps or information required to go from one step to the next, so that you don't have to have those rules being written manually. Does that make sense?
It does. The last one that I'd like you to help us with is one that I think is right up your alley based on your background, and that is natural language processing, or NLP. Tell us a little bit about how that works and how that fits into this mosaic of different concepts.
Sure. And as I said earlier, this is what our company works on. So indeed, this is what we've been focusing on for a couple of decades now. So natural language processing, in the most basic description, is a computer program that can take in text information or language information created by people and come up with some result, come up with some analytic information about it. And there's lots of different types of information you might want to get out of that, ranging from what I consider the most basic kinds of things we do, which is what languages are written in. And that's kind of, as I said, at the low end. And at the high end, or the most complex form, what are some sort of semantic interpretation of, say, a query to a search engine, and using that semantic information to find documents that have that same semantic information, but maybe not the same terms. We call that semantic similarity in our particular implementation. And to extend that high-end concept a little bit further, to be able to do that across languages. So wouldn't it be cool, for instance, if you could go to a search engine, type in a query that says drug companies, and find, say, Japanese pharmaceutical vendors. And in fact, that's very possible. So the software that does that is the NLP technology, and there's a wide range of capabilities in between those two extremes I just gave you. This is useful in really a wide variety of places. I'm not going to go into a sales pitch on it, but just to give a little bit more color, the search engine example is very tactical, and NLP tech is employed a lot by search engines to do the kinds of things I just described. It's also really useful in the intelligence community, for instance, to try to boil down a lot of the information that's out there and turn it into something that's more actionable, maybe by building some sort of model of the universe that's in a structured form that a computer can work with.
Okay, well, that's really helpful. Now that we've got at least a rudimentary understanding of some of the key vocabulary in the AI space, can you help me understand, give me and my listeners, our listeners, a brief history of artificial intelligence? It seems like it's, in some ways has sort of appeared fully formed in front of us just in the past few years, but I know that's not the case. So can you kind of walk us through a little bit of the recent history?
Sure, and that's another really good question, because the idea of artificial intelligence has been around as long as we've conceived of building machines. You can think back to even the 30s when the first notion of robots as being a sort of an exemplar of where physical machines could go. The idea that you had somewhat sentient robots was already showing up in movies in the 30s. The actual more realistic development of AI tech started with the advent of the computer era, which I would date to the mid-'60s. And from the very start, there was a notion that, we could program computers to do virtually anything. And there were early attempts to do that, and in fact, early development of not only the notion of artificial intelligence, but some of the basic concepts. The idea of neural nets, which I didn't mention earlier, but neural nets are behind a lot of these AI technologies. That also stems from the 60s, if I recall, at MIT. One of the first artificial intelligence type programs was written circa, I want to say, mid-'60s, and it was a program called ELIZA, or frequently referred to as Doctor, which was essentially a simulation of a psychoanalytic session with a psychologist. And it was very primitive and relied on just a number of, I'd say, handcrafted rules. This was a very short in terms of how the program was, and a very limited number of rules. But in the first 5 minutes, if you type things into this, you could almost squint your eyes and imagine you were having a session. You would be able to type things like, I am concerned, I'm worried about my mother, and it would respond with very primitive responses based on the fact that you mentioned your mother, and say, oh, you're talking about your mother, how does that impact you, or something like that, where it was a really simple rule. The simple rule was, if you see the word mother, respond with this sentence. That was the first wave. And that first wave was impressive enough that people started thinking that the AI was going to develop very rapidly. And we had the first wave of AI expectation, which didn't happen. AI, the software, the hardware, nothing was really ready for AI in a really impressive way to develop then. Then in the mid-'80s, it kind of happened again. The software and the hardware had gotten a lot better, and the ability to process a large number of these handcrafted rules written by experts was much more powerful, but it was still very limited. And it was limited because they still had the notion, as late as the 80s, that artificial intelligence was going to be a human rewriting their knowledge set, their knowledge base, into these rules and putting them into a computer. And the problem with that is it was always going to be fragile, and the rules were only going to be as good as what the human had thought of to date. The limitation was broken through, and now, and this is really in the last roughly 15 years, by virtue of these machine-learned approaches that I described earlier. The beauty of the machine-learned approaches is that you don't need a human to describe what a dog is. You don't need a human to describe the whole interaction with a psychologist. All you have to do is have these examples we talked about where a human says, if I see this input, I would call it, give it this output. And then the computer essentially, in these models that I'm talking about, the computer essentially figures out what those rules are. And it figures them out based on patterns that a human might not have thought of, and embeds them in these models are very, very large models that have a lot of different interactions happening within them. So, net is we're in the third and a half wave of artificial intelligence where from very good ideas started with back mid-'60s, and we finally have hit the point where we have three things that have come together. One is the hardware. Computer hardware is way more powerful, obviously, than it was 50-plus years ago. The software, the ability to build software, is also many times more powerful. And the modeling approaches, these statistical modeling approaches, are way more powerful than we had. These three capabilities come together to produce the ability to build actual effective AI technology here in just about 2020.
Much of the use of AI and NLP to fight crime and terrorism really has been led by the intelligence community, and I know you've spent a number of years helping them do that. Can you talk to us a little bit about when financial institutions began using these technologies to interdict financial crime?
So I'll start by giving an idea of when the intelligence community started. And the intelligence community and the likes of DARPA actually funded quite a lot of the development of these capabilities. A lot of it in our domain, human language technology, or NLP, stemming back to the early 90s. And the intelligence community actually, in many ways, was on the vanguard, led not only the development but the deployment. So many of these approaches towards analyzing large bodies of textual data and coming up with some sort of extracted information models have been applied for national security since the mid to late 90s. rather old time, getting from roughly 2020, the finance community, as we observed it, came in a little bit later, and a lot of this was the finance community and a lot of the commercial applications had higher expectations for what I'll call just outright binary accuracy of things. They were coming at it from a different perspective and needed to have 100% confidence kind of notions. And it took a while. First of all, the technology had to get better in the ways that I've described. But the other thing that had to change was expectations about what it means to be accurate. And so I think that the real transition, to finally answer your question, the real transition has been over, say, the last 15 years. So it kind of lagged or learned from the intelligence community and national security by, say, 10 or a dozen years.
And how do you see these technologies being applied to anti-money laundering and financial crimes today?
So I'm going to divide these AI technologies into two categories here to make it really simple. I'll call them low level and high level. That's not a term of art. That's just sort of an artificial delineation. At the low level, there are basic capabilities that are being deployed, have been deployed, as I said, for maybe 10 or a dozen years, to solve very tactical, specific problems. One example is working with watch lists and the very fundamental sounding problem, but very hard problem, it turns out, of finding or matching names as they appear in, say, an onboarding data set to names in a watch list. They say it's matching one name to another sounds like a really straightforward, I'd say almost trivial problem. It's not. It's not for a wide variety of reasons, stemming from the fact that names actually vary a lot in the wild, in the real world. They vary because people write them wrong. They vary because they borrow from another language and are written different ways. They vary because there's nicknames. John and Jack are are two different ways of writing the first name of the same person, and yet they don't look like each other. And so there's a lot of sophistication required to do that, and AI techniques have and are being deployed to solve that problem today. That's very tactical, very real. And that's a low-level example. And there's quite a few others. If you think about linear regression and how it's been applied to look at things like transaction modeling and looking for transaction pattern detection and the like. At the high level, we look at connecting the dots between different types of information. And it's out there, it's being deployed a lot less because the capabilities are a bit less mature. But looking at information across silos, it's a classic problem. Everyone in IT has this in so many different ways. That's one dimension of the problem, but we look also at looking at not only across silos, but at looking across style or genre or type of information and being able to connect that data. So, for instance, to be able to connect the dots completely between, say, some transaction sequence with external data sources like maybe watch lists and due diligence information and what the government that we call OSINT or open source intelligence, which is information publicly available, like maybe news sources and or social sources. To be able to connect the dots across all of those sources in some meaningful way, resolve the information to determine, say, that you're talking about the same person across 5 different types of sources, and use that to come up eventually with an actual decision, where that decision at this point is pretty much always is and should be in the hands of a person. It's a very vague description, but that's how I see it. That both these high level and the low level capabilities.
And how do you see these applications evolving in this space over the next 3 to 5 years? We're obviously in the middle of what you said is sort of the third and a half generation of AI. It feels like because of the things you talked about, machine power, programming power, and data analytics, that things are accelerating in terms of progression. So what are we going to see over the next 3 to 5 years, again, in the financial institution or financial services space?
Okay, sure. Well, the first trend is kind of a gimme in a sense that I've never heard anyone argue against it, and that is that there's going to be a growth in the quality, quantity, and velocity of data, just broadly speaking. There's absolutely no one in any area of information technology who would argue with that. And so just having a vast growth in that velocity and volume of data means that you have no choice but to increase your use of various and sundry forms of information technology, including AI. There's just too much information not to increase the depth that you dig, or the depth of type of technology that you use. The other thing that I alluded to is the variety of data, and there's a lot of new types of data being applied. You see the non-traditional credit scoring approaches in newer financial institutions. So that gets to the point I made before about connecting the dots between different silos and different types of data between the different silos. To be able to do something intelligent with this non-traditional credit scoring, connecting it to your existing problems like AML, and to be able to connect in to do the screening for your non-traditional scoring process against an existing, I'll call it traditional score AML watch list data or AML process. That's going to be a challenge. And you're not going to get there without, again, upping the game on the types of technology you use to do that. The other thing I would say is to emphasize this cross-silo, cross-data type analytics. Right now, the techniques for, say, due diligence review largely depend upon an analyst to do that cross-data integration, to make that determination. So they're mostly focused on using tools, some IT tools or whatever, to put really good information in front of an analyst and then ask the analyst to read it and make a determination of some form. Does this need to be escalated? What do we do with it? We need to and are adding technology to provide a boost to that. I still expect that people will make that final determination, but to be able to maybe put some scoring around that or improve the quality of information we put in front of that analyst so that they can do a more efficient and more effective job, that has to happen.
Do you expect that those types of applications that you just described are going to be deployed as add-ons to existing transaction monitoring systems, or do you expect that we're going to see new systems being deployed where the architecture is really built on AI, on an AI platform from the ground up?
So that's a good question, and I think the answer is actually very simple. Yes and yes. It's going to be both. There's no particular reason why we can't add these tools into existing workflows. In fact, given how many existing tools, technologies there are out there and how deeply embedded they are in a lot of financial institutions, that's absolutely a requirement. That said, there will certainly be plenty of instances where some organization is going to come with a completely ground-up solution, and it'll probably take a while for those to get deployed, just a normal IT development deployment cycle. But there clearly there'll be advantages if you have new techniques such as AI built across the board. So it's kind of a mediocre answer, but as I said, it's yes and yes.
Okay, well, I'm not an expert the way you are, but I would agree with that, certainly in the near term, the idea of bringing on fully formed AI-based systems to replace what's there, those aren't ready yet, and the migration path from one system to the other is a very daunting task, particularly for large organizations. And historically, the huge challenge has always been with any of the large surveillance systems is really having high-quality, consistent source data from all the different places that you want to feed so that whatever the system is doing, whether it's traditional rules-based or more sophisticated than that, it's got everything that it needs to munch on to come up with some kind of an answer, whether it's an alert or something more sophisticated.
Just a quick comment on that. Across the board, across many applications we deal with, honestly, one of the biggest problems has been, is, and I think will be for a long time, data quality. You mentioned that very briefly there. In computer science, we've long had this expression, garbage in, garbage out, which says that if you don't have good input data, there's no way you can expect good output data. And when I talked before a couple of times about integrating information across silos and across data genres and forms, if any of that data isn't trustworthy, at least to a very high confidence, nothing is 100%, but if it's not trustworthy, then the game over at the very start, and that will continue to be a problem. So it is worth mentioning that AI tools are being deployed to help in the data quality space. Fixing data quality is nothing new, as I said, and there's a lot of value to using some AI tools to help there as well. That name match technology I referred to earlier, for instance, helps to mention of this data quality. If you have the same appearing in lots of different ways, a name matcher, high-quality AI-based name matcher, can be used to figure out that it's the same name and maybe to link up some records so you can clean up some duplicate records. Just one example there.
Given the likelihood in the near term in particular that AML compliance professionals are going to be asked by their system vendors to evaluate the possibility of a new AI-based add-on tool, what are some of the key factors that the AML professional should be looking for so that they can sift through the various offerings and pick out the ones that are going to be give them the best leverage?
Very good question, and something we spend a lot of time with our partners and customers on, because evaluating technology like these AI systems or NLP in particular, evaluating this kind of technology which is not 100% anything. I didn't emphasize that before, so I'll say it now. You're talking about these ML, machine learning techniques. They are statistical in nature, and they're dealing with data that is very messy, human language information for NLP. There's no 100% available. And in fact, one of the things we pay close attention to is what is the highest quality that a human could give you on any given human language analytic task? This is a really good question to have people reflect on. Now, I'll ask it to you. How well do you think you could identify the parts of speech in a sentence? Remember parts of speech? You learned them back in grammar school. You don't think about them much. But if I gave you 10 sentences from a college text and said, what score or what do you think you'd get identifying the parts of speech across that, how well do you think you would do?
Somewhere in the 40-60% range, but I think part of that is when you learn a language as your first language, knowing the parts of speech is really helpful. But as you mentioned, we don't really teach children the parts of speech when they're learning language at 8 months, 10 months, a year. We wait until they actually have the language pretty well managed, and then we show them, oh, by the way, it has this structure.
Yes, that's true. And I found that learning foreign languages, I paid much closer attention to grammar because I already had a notion of grammar and of things like parts of speech. But you probably, honestly, you do better than 60%, I suspect, but you wouldn't get very close to 100% probably. And very few people who aren't editors would get, much higher than, say, 95%. And those kind of numbers for a very simple task, and part of speech is a very simple task, are very relevant when you think about what are we asking these computers to do and how accurate should we expect them to be. Well, if we're using information tagged by a person, is part of speech, tagged by people, and that maybe is as accurate as, say, 97% correct, when we know from a start that we can't expect this computer model to be more accurate than 97%. That's as good as it gets. And for some of the more complex tasks, maybe 93% or even lower is as good as it gets. And so right out of the gate, the first thing we talk about for evaluating natural language processing accuracy is you can't get better than the input data, that garbage in, garbage out notion that I talked about before. And so how accurate can one of these processes be? Well, if you're 95%, you're probably doing pretty well. And that sometimes for people who are imbued with a notion of computers being these mathematical things and expecting a binary, they're either right or wrong, that's a new way of thinking about it. I think about it from the point of view of if we think about computers being these math machines, and they are, historically we've thought about them being algebra machines. They can do equations. And when you think about algebra, you think you come to the belief that, there's a right answer and there's a wrong answer. Certainly your algebra teacher told you that, right? And so you can get 100% correct on a set of algebra problems. Well, AI and machine learning are not computers as algebra machines. They are computers as probability and statistics machines. And so we have to think about them in a probabilistic way. And that's essentially the first learning that people working with this kind of technology have to get to, is an expectation that you have to think about it probabilistically. And when you do that, the next thing you look at is, well, what is our accuracy now? And I suspect most financial institutions actually think about this. They may not measure the accuracy of their human evaluation processes, say for AML screening, but they would understand it. And if they did measure it, honestly, I don't think they'd mostly be in the 90s. I'm not picking on anyone here, but humans doing complex tasks fall down and make mistakes. And so that should set your baseline, right? Really the baseline should be we're going to measure our accuracy as a starting point. What is our actual accuracy now? And let's evaluate how good the computer system is, the AI system is, at doing the same task. And if it's better, that's great. But better won't be 100%. That's kind of a soapbox position that I have. I've been through it many, many times in a bunch of different domains. And it's very helpful. It's helpful from the start because we go in to our customers and say, how are you measuring your accuracy? And on a good day, they have an answer to that. On a typical day, it's a very ad hoc thing, and we work with them to develop an actual mathematical accuracy measure.
Well, I think that's very helpful because one of the challenges that we all face in the industry is an expectation around receiving a significant benefit for the costs involved in major systems and being able to understand what it is that we're actually getting today and whether or not the next add-on, whether it's AI-based or not, is really an enhancement in terms of quality of output, throughput, and other things that can be measured, although some of them are quite difficult to measure accurately, and I think many of them, because of the difficulty in measurement, go unmeasured. It'll be important for us as an industry to really go through the process of understanding what is our current baseline, so how will we get an enhancement. So we're just
Exactly.
We're just about out of time here, but the last thing I'd ask is, if you've got some final comments about what other expectations or opportunities the AML community should be looking for from these technologies as they evolve over the next, into the future, I guess I would say.
Oh, sure. So something I mentioned earlier, and it's an important point, is these technologies are here now and they are deployed and useful now. And they are deployed at a variety of levels. I talked about a high and a low end of capabilities before. Absolutely, they're being deployed and have been for quite a number of years at the low end. Some of these basic functions that are used just to improve some sort of analytic computation using AI as part of the system. We're in kind of, I guess I'd call it a Cambrian explosion of new ideas, new models, new ways of using these technologies. And when you're in the midst of that, there's a lot of experimentation to be done on using the higher level capabilities and using them in very different ways. And I believe that financial institutions and everyone else should be trying experiments. And, going from experiment to deployment, of course, takes a while, but the experiments are very educational. Understanding that the experiments often will fail, that's why we call them experiments, for testing a theory. So those are sort of the internal focused parts of this. The other part we didn't touch upon at all is where are the regulators on all of this. And this is really interesting. There's a lot of movement on the regulator side, and it's very positive. I think they started kind of slow, but when you go to, say, ACAMS and listen to what they're saying from the regulator side or attend a RegTech forum, the regulators are there. They understand all of these issues, and they understand the need for deploying these technologies, and they're looking for ways to build, say, sandbox environments and relax or at least come up with ways of interpreting regulations to give the financial institutions a chance to try things out, because they appreciate that there's a whole lot of failure in financial crime screening and AML screening. Right? Everybody knows this. The numbers are scary in terms of sort of how successful things aren't. And so there needs to be creativity, and I'm really encouraged to see the regulators trying to be on the forefront of this.
Steve, I want to thank you for your time and your insights. This is a very exciting and rapidly evolving space. It's also can be very opaque for people who don't necessarily have a deep technical background. And as you pointed out, some of these technologies are really coming to us from somewhat different direction than the technologies we've been using for many years. So I think it's really helpful to have an expert like yourself to be able to speak to
help begin the process of demystifying so that people can feel like they're smart enough about these things to make good choices and to know the right questions to ask as they go forward and have to make judgments about which ones to use and how to use them effectively. So again, thank you very much, and I look forward to speaking to you again in the future.
Excellent. Thank you. It's been my pleasure.